Hello, everybody. Welcome to the daily highlights of Falling Walls in Berlin Science Summit. My name is Astrid Frohloff. I'm a German TV moderator and journalist and have the pleasure to guide you through this session. In the next 15 minutes, you will get a short overview about what's coming up in our diverse program. You get some recommendations, you meet some outstanding speakers, and you get a good idea of how to create your personal schedule. Our first take is an interview with an expert from the life sciences. Now I would like to introduce to you somebody who is a rising star in the scene of science. His name is Phil De Luna, and he's one of the top researchers in the growing field of clean energy, featured in the Forbes 30 Under 30 list for energy and a Carbon X Prize finalist. He will talk with us today about his work for the National Research Council of Canada on hydrogen. Hello, Mr. De Luna, nice meeting you. What is about hydrogen that you find so fascinating?
Well, hydrogen is a clean fuel, and it could potentially be the fuel of the future. When you combust hydrogen and use it, the only emission you get from it is water. So you could imagine in a future society being able to replace the majority of our fossil fuel use with hydrogen. And this is particularly important for areas which are hard to decarbonize with electricity alone. Hard to abate sectors like transportation or manufacturing, the sectors that contribute so much to our quality of life. If we can find a way to move past fuels that emit CO2, then we can find a way to potentially go to net zero even faster.
Well, if you look 10 years ahead, what would you think our energy system and our transportation infrastructure will look like?
Right, that's a great question. And I want to begin by saying that hydrogen is just one piece of the puzzle. When we think about the energy transition, there are many different technologies that need to be at play. Battery technologies, renewables like solar and wind and hydroelectricity, nuclear technologies, whether that's small modular reactors or next generation of plants. We really need to think of a whole approach, a holistic approach that makes the most sense in different jurisdictions. In Canada, for example, where we're blessed to have a relatively clean electricity grid, it makes a lot of sense to try to make hydrogen in jurisdictions like Quebec or British Columbia, where we have an abundance of hydroelectricity. Hydrogen is really only clean if it's produced from electricity that in and of itself does not emit CO2. And there are different ways to make hydrogen. And this is kind of the biggest bottleneck right now, which is how do you produce hydrogen and do it in a way that does not emit greenhouse gas emissions? So in 10 years or in the future, I hope to see a big push towards a change and transition in our energy systems, where we have renewable energy capacity like solar and wind and hydroelectricity abound. And then we have renewable to hydrogen technologies where we can then capture that renewable electricity and store it into a hydrogen fuel using these new technologies. And then at that point, we can have distributed hydrogen, distributed energy. Why is this important? It means that we can reduce all of the emissions that you would normally see from large-scale transportation, like air flight or freight or trains or trucks. And this could be potentially extremely exciting for helping us get to our net zero goals.
Well, that sounds like a great vision, but I guess there are some obstacles as well to reach this goal, right?
Yeah, absolutely. Make no mistake, this is going to require a massive amount of investment in infrastructure. And on top of that, there are a massive investment in research and development and science, quite frankly. The International Energy Agency released this year its Energy Technology Perspectives report for 2020. They analyzed over 800 technology pathways, and they found for us to reach net zero by 2050, almost half of the technologies needed to reach this goal are not yet commercial, which means they are either in the lab or at a prototype or even at a pilot demonstration. So there needs to be a massive amount of investment, not only in actually scaling up the infrastructure for transportation of this clean hydrogen, for the production of this clean hydrogen and the utilization, but also on the underlying technologies to help us get there. It's going to take a lot of work. And one of the biggest issues right now is getting the cost down to move, produce, and use hydrogen. At the heart of this is new technologies and catalysts that can convert energy into hydrogen, or membranes or systems. So there's a lot of work still to be done, but it's a very exciting time in the field.
Yeah, I guess so. And we're looking forward to learn more from you in one of the sessions at the World Science Summit. Thank you so much. It was a pleasure talking to you, Mr. Luna.
Thank you so much.
So what else can we expect in the next 24 hours in our program? Let me give you a short overview. We've got a great event on climate policies, for example. In this lecture, you learn how climate policies are implemented in different countries and regions. Means you get an international perspective on how governments, NGOs, and the private sector are underway to broaden the Paris Agreement on climate change. The Quantum Future Award, what is it about? The Federal Ministry of Education and Research honors outstanding master and PhD theses dealing with applied quantum technologies. Watch the 10 pitches and be there to meet the award winner in 2020. How can we make our societies more resilient in times of a pandemic? Of course, one of the key questions in these times. In this panel discussion, you will get scientific responses by experts. They will talk about ways how to build resilience and support health and sustainability in the wake of COVID-19. So one of our overarching themes in the summit is artificial intelligence, and another event is dealing with this issue. How AI research makes us rethink our intelligence. In this session, you will discuss how concrete findings of AI research make us rethink such questions. You may participate in this discussion as well. So another one is Astronomy aktuell mit Datenvisualisierung. So this one is in German. The director of the Planetarium Berlin, Tim Florian Horn, will guide you through the night and report on space's probes, shooting star streams, comets, and current discoveries in astronomy and space travel. And the last one on this table is Science Film Rules with Ski Film It. This is a hands-on workshop to discover the rules to science filmmaking that will turn the science film into a masterpiece. If you would like to attend, please book the spot in advance. Find more information on our homepage, and you will see there is a calendar function as well. You can use it to mark the events you would like to visit. So I've got another question for you. Can plants be political? Artist Zheng Bu is convinced they do. Tomorrow at 1 o'clock Berlin time, Zheng Bu, Artist in Residence 2020 at the Gropius Bau in Berlin, will be joined by biologists and ecologists to discuss how plants in practice do politics. So learn more about this. Here is a video.
My name is Zheng Bu. I normally live in Hong Kong, but this year I'm here in Berlin because I'm the artist in residence at the Gropius Bau. I'm not a scientist, I'm an artist. My primary concern these years is the climate crisis, and also I would call the extinction crisis. I think in order to address these really planetary crises, as artists, I have to work with scientists, but I also work with people in humanities, in social science, etc. Because I think it's, in order to address these large issues, it's really something we have to come together from all the disciplines. In the event, it will be conversations between me as an artist with plant scientists. I think the conversation is very important because we have very different approaches. I'm interested in how scientists study plants, what they have learned about plants. I'm learning from their research. I'm in conversation with them to kind of think about how we can see plants differently, how we can understand their existence, not only as biological, but also as political, because we tend to see our life as not only a biological existence.
So one thing you should definitely not miss are our Falling Walls circle tables, where leading scientists and policy makers from different fields discuss about how to set the post-corona agenda, and they will give a broader picture on current challenges. So our next circle table is discussing about future computing. Can we remain on a stable democratic course in the long run if autonomy in IT continues to dwindle? What does this mean for Europe? Who will be the major actors in the future? So tremendously important questions will be discussed in this panel. So one element in our highlight are our daily stories by photographer Herlinde Kölbel. She visited great scientists all around the world and she brought back amazing pictures and amazing stories. At Falling Walls, she talks about her encounters.
Today we're looking at a portrait of Antje Boetius. She's a German marine biologist and director of the Alfred Wegener Institute that was at the helm of an unprecedented expedition into the Arctic, researching climate change there. So, Herlinde, what's the story behind this portrait?
Antje Boetius were very much influenced by the adventure story of her grandfather. He was a sailor and had many stories and dangerous stories to tell. But also she was influenced by her mother and grandmother, two strong women, and they told her that for girls, everything is possible. And as a child, she also wanted to be an astronaut of the Earth's interior, and she fulfilled her dream and was 30 years on ships and made 49 expeditions. She also recognized that you have to create new big ideas, not to work on little things. And her philosophy is also, give the coincidence a chance in your life.
So that was our daily highlights. Please stay tuned since we will continue immediately with our winner sessions. Today you will meet the top 10 winners in the categories Physical Science and Science Startups. So stay tuned. I'll see you in a minute. Bye. Hello everybody, welcome to the Falling Walls Winner Sessions. I'm glad that you're joining us here in Berlin. My name is Astrid Frohloff, I'm a German TV moderator and journalist, and I have the pleasure to guide you through this session. Over the past months, more than 900 nominees from all around the globe have made their journey to become the science breakthrough of the year in their respective category. We've got 10 categories all in all, and in this session we will introduce the top 10 winners of the category Physical Science. And in the studio, I'm joined by Dr. Adam Levy, my co-host. He's a physicist himself. He is a science journalist, and he did the interviews with the winners, so he got great insights into the breakthroughs. Talk to you later, Adam. I'm also very glad to welcome Daniel Seifmann. He is the jury chair of this category. He's professor of physics at the Weizmann Institute of Science in Israel. It's a pleasure to have you joining us online. So each category is overlooked by a distinguished jury. All the jury members are very prominent experts and leading scientists in their respective fields. Here you see them on this table, and we are very grateful for their support and their contributions here in the jury. So Daniel, you are chairing the jury. To kick off this session, could you tell me what are the things that are fueling your fascination for physics?
Well, that's a very good question. In fact, the movie we just saw before you start speaking was of a magician. And since I was a kid, for me, physics was magic without any tricks. I mean, I think that's the fascination. In fact, you see, we're speaking to each other from 5,000 kilometers from each other, and it seems to work perfectly well. Behind that are lots of physics, which looks like magic, but there are no tricks. It's just real reality. And so for me, the fascination of physics was we could make things amazingly sophisticated based on very fundamental theories that describe the world. Mm-hmm. And from these descriptions, we can really make things working and, of course, improve life of people. So that's really what tricked, if you want, my imaginations.
Right. What are the biggest trends and potential breakthroughs in the physical science? Can you see any interesting patterns?
Well, I think we are now living in a new revolution, which is what I would call the second quantum physics revolution. The first one basically started 100 years ago. This is the one we're using right now to speak to each other. The electronics we're using is based on a revolution that started in physics 100 years ago. The transistors, the electronics are all based on discoveries, mostly solid-state physics, but not only, photonics, light, and so forth, that allows us to use technologies that, computers and cell phones and etc. The next revolution, the quantum revolution, will be an amazing one. It will take still some time, and I'm sure everyone has heard about quantum computing, which basically will allow us to solve problems that we think are unsolvable today. There are many problems unsolvable by whatever computer you can have. Even if you have the most powerful computer in the world, and even if you have a computer which would be 10 times stronger, it won't even solve that problem. And all this quantum new revolution will create a change which will be like the change we experienced for the last 100 years. Using the technology we use today is unthinkable 100 years ago. Using the new technology of quantum physics will be unthinkable in 100 years from now. So that's really the trend I see. There are many reasons behind that. And of course, some of the winners in this category have been touching on this field. So it's very, very relevant. Exactly. What is being done in this competition.
Yes, and we will have a look at the winners. Thank you for the moment, Daniel. I would like to ask Adam, first of all, Adam, since you are holding a PhD in physics, what did you take away, all in all, from the talks you have led with winners?
Well, it's really been a reminder of that magic, but also of just how varied the physical sciences are. Among these talks, there are topics which are close to my heart, some even close to research that I carried out. But there are other topics which I really hadn't encountered before, and it was fascinating covering this broad breadth of a subject.
Okay, so then let's see who the top 10 winners are in the category Physical Sciences. I'm glad to announce the first winner. Christel Michielsen from Forschungszentrum Jülich, Germany, doing research on practical quantum computing, as we just have heard. How did the jury judge about this project, Daniel?
Well, this is, of course, an international project which picks up a lot of people together. But what she did here was actually to make the comparison, or to make possible the comparison between a quantum computer and a classical one. It is fine to build a quantum computer, but to see that it's really useful and could actually do something, it really had to beat a normal computer. And she demonstrated that indeed the quantum computer they built was able to beat a normal computer. Quite an achievement. In fact, the beginning of what I call the quantum computing revolution. So that's how we make a judgment, and it's really top quality work, no doubt.
Okay, let's learn more and watch a video now.
Breaking the wall to practical quantum computing. Christel Michelsen, Forschungszentrum Jülich.
My research is about quantum computing. So what we do is simulating quantum computers and quantum annealers, and for this we use supercomputers. We use the quantum computers also to run some simulations on, and together with the conventional computers, we can then benchmark them. So we can see how well the quantum computers that we have nowadays perform for certain tasks. And then I come to the recent breakthrough in my research, and that's quantum supremacy. It marks the first moment where a quantum computer can perform a task better than a conventional computer.
Now, why is a quantum computer something that we'd actually want to develop in the first place?
With our conventional computers, we certainly reach some limits. So some problems cannot be solved at all with a conventional computer, or not fast enough, which is often the same. And therefore, we are looking for new computer technologies. And one of these new computer technologies that is promising are quantum computers.
Now, in the future, do we see it as quantum computers replacing things like the laptop that I have in front of me, or are quantum computers really specific to specific tasks?
It will definitely not replace our laptop. A quantum computer will be a computer that we also have in a supercomputer center like ours, and which can indeed perform certain tasks. What we hope is that we can integrate quantum computers with conventional computers, so that it becomes a kind of accelerator for the conventional computer.
And how does it feel for quantum computers after being worked on, well, really for decades, to now finally be fulfilling this dream of outperforming conventional computers?
That's of course very exciting, but as researchers we know that there is still a lot of work to do in order to make from a quantum computer a computer with which one can make production runs. So really simulations for real-world problems.
And how would you actually describe the differences between a quantum computer and a conventional computer like my laptop?
Conventional computer works with bits. They can take values 0 and 1. And a quantum computer works with what is called quantum bits or qubits. And qubits do not only take the value 0 and 1, but so to speak, it can take any value in between. Now, another property of quantum computers is that they are having what is called quantum parallelism, meaning that they can do a lot of operations in parallel.
And do you have any estimate for when we might be able to expect a quantum computer to be making a difference for real useful applications?
The quantum computers somehow surprise us. We know we still have a long way to go. There are still a lot of technological problems that need to be solved, and there are also some fundamental ones. So for a researcher, this is a very exciting field nowadays.
So congratulations, and all 10 finalists in the category made it to the top, and that's a good reason to congratulate all of you. But let me mention the journey is not over. We've got 10 categories, and the jury will choose one winner out of each category. And on November 9th, the day when the Berlin Wall came down, we will celebrate the Falling Wall's breakthroughs of the year 2020 through all categories. So now let's announce our next winner. Let's move from Germany to the United States. And the winner is teaching at the Massachusetts Institute of Technology, and her name is Sarah Seeger. She's aiming for breaking the wall to life beyond Earth. And I'd like to ask the jury, what is your explanation?
Well, as you said, I mean, I think the holy grail of our civilization sometime would be to find another civilization, right? We are so much used to the fact that we are alone in the universe, which in my opinion is probably wrong. So what would be the action of the society or all this planet if we could say we discover life outside of planet Earth? I think that would be a tremendous headlines, probably the biggest headline we ever had. So in this case, this is a researcher who is looking for life outside of Earth, what we call extrasolar or extraterrestrial life. And she's using very sophisticated tools to do that. And I think we look at the tools and the techniques which are being used, and we're amazed by how much advance has been made. Of course, life has not been found, but the techniques have been developed, and I think this is the way to go.
So we're excited to see the interview with her.
Breaking the wall to life beyond Earth. Sarah Seeger, Massachusetts Institute of Technology.
My research breakthrough started just over 20 years ago when I invented the main way that astronomers study exoplanet atmospheres today. An exoplanet is a planet orbiting a star other than the Sun. We know of thousands of exoplanets, and there are millions, billions, trillions more out there in our galaxy.
So how do we begin to spot planets going around other stars and then to peer inside those planets' atmospheres?
The most popular one today relies on transiting planets, planets whose orbits are aligned just so that the planet goes in front of the star as seen from our telescopes. Astronomers are able to monitor tens of thousands or even millions of stars at one time, searching for the tiny drop in brightness that might indicate it's a planet going in front of its star. Now, when the planet goes in front of the star, we can use another technique, using different telescopes than the ones used to actually find the planet. Because when the planet goes in front of the star, some of the starlight shines through the atmosphere. And just like shining a flashlight through a fog, some parts of the starlight make it through, and some parts of the starlight do not. And specifically, we can look at the spectrum of the star. And by seeing what parts of that starlight make it through and which parts of the starlight do not make it through the planet atmosphere, we can actually infer what gases are present in the planet atmosphere.
For you, how has this work studying exoplanets changed our understanding of our own place in the universe?
Finding planets in general and studying their atmospheres, it has taught us that our planetary system might be quite rare. We have not found any solar system copies. That's partly because nature has given us so many types of planets. A giant planet where an Earth should be. Some planets, even small ones that are Earth-size, are so close to the star that the surface temperatures are hot enough to melt rock.
When do you hope we'll be able to do this kind of work and start to answer this really fundamental question? Is there life on other planets going around other stars in the universe?
With the next generation telescopes, we'll have the first capability to answer those exact questions. It's the very large ground-based telescopes now under construction who have effective mirror diameters of 20 meters, 30 meters, 40 meters. And it's a really special, new, sophisticated type of telescope we're hoping to build and launch to go to space and to block out the starlight so we can see the planet directly. If planets are common that have water and life, we should be able to find them in the next decade or two.
What are you most excited about right now in terms of planetary research?
Today, I am most excited about the planet Venus. Venus has sometimes been called Earth's sister planet, but it is nothing like Earth. Venus is so hot at the surface, it could never support life. But away from the surface, up in the clouds, Venus is cool, and it's actually the right temperature for life. It's a very fringe topic people have been interested in, starting with Carl Sagan over half a century ago. But more recently, I became involved with a team that discovered phosphine on Venus, a gas that doesn't belong, and that on Earth is only associated with life in oxygen-free environments. So I'm leading a concept study about a space mission that would go to Venus and drop into the clouds and search for signs of life or even life itself.
That's fascinating. Adam, what significance do you see in this research?
Well, it really is amazing. I think it just completely changes our understanding of our relationship with the rest of the universe. Just a couple of decades ago, we didn't know whether our solar system really was unique in having planets. Now, there are thousands and thousands of planets we know are going around other stars, and the fact we can begin to hunt for life on these planets, yeah, it's just a complete transition in just a few years, really.
Yeah. Let's have a look at the next winners. The next winner I would like to announce is Andreas Wallraff, ETH Zurich. He wants to break the wall to efficient quantum computing. What did the jury convince most about this research, Daniel?
Well, we are back to quantum computing. And actually, as Crystal said, there are some fundamental issues. It's not only about building and the technology that we need to build such a computer. There are some very fundamental issues related to quantum physics and the fact that these computers have a lot of errors, what we call faults. And what Andreas has been doing is trying to understand how one can improve, in fact, the error corrections of all these systems. Without that, there will be no room for quantum computing. And again, the idea is putting into the fundamentals of quantum computing, not the machine itself, but the fundamentals. It's very critical and very new, and we were very much impressed by these original ideas.
So let's learn more about his work. Here's a video.
Breaking the wall to efficient quantum computing. Andreas Wallraff, ETH Zurich.
Our lab does work on realizing quantum computers with superconducting circuits. And one of the aspects that we know about these quantum computers is that we will actually need to assemble them from various elements. And we have come up with a new idea how to bring different processors together through a so-called quantum link.
What actually is a quantum computer? What makes it special when we compare it to conventional computer like the laptop I have in front of me?
Conventional computers, they represent all the data in bits. Those bits can be zeros and ones. And in quantum computers, you can use the special features of quantum physical objects that they can be in a superposition of zeros and ones. So that gives the quantum computer more freedom to do more complicated calculations more efficiently than a classical computer.
And do we imagine that quantum computers would replace all the conventional computers we have now, or are they for particular tasks?
Our current understanding is that more likely quantum computers will supplement conventional computing for special problems. Yeah? For example, problems that relate to simulating materials or doing quantum chemistry calculations to develop new drugs or new fertilizers. Or maybe looking into optimization problems, like, for example, when you assign airplane crews to planes and planes to gates at an airport, for example.
Now, why do we need to link different quantum chips together? Why can't we just build bigger and bigger quantum chips?
Building bigger and bigger quantum chips is difficult because you fit a finite size of qubits, the elements which you do your quantum computation with, on that chip. And you could then still consider combining several chips in the same refrigerator and operate them there simultaneously, but eventually you will run out of space in that refrigerator, and it will become more convenient to actually distribute your chips over many refrigerators and then connect those to each other in a similar way as you would connect computers in a cluster in a computer center to each other.
And why is it actually challenging to build these quantum links?
Yeah, one of the problems really is to operate them at these low temperatures. So far, many labs and startups and also information technology industry has operated these refrigerators for quite some years, but nobody had really connected different one of these refrigerators to each other while keeping them really, really cold in the connection. And we achieved a cold connection that is about as cold as the inside of the refrigerator itself. And we've been able now to take two of these refrigerators in their vacuum cans and connect them to each other with a horizontal link that can also be cooled down to this very, very low temperatures.
And what are you hoping you might actually be able to achieve by creating these quantum links?
So this will be an additional path that allows us to build more powerful quantum computers than we can have now. So both our lab in an academic setting at a university, but also IT industry like Google and IBM, they're working on this problem. And currently all the solutions that they look at are actually looking at building processes in a single cryogenic system. And like our new approach will allow to bring those different systems to each other into a larger quantum computer cluster. And that is a new thing, a new realization that we have made and realized in our lab.
Well, I'm wondering, Adam, we've heard a lot about quantum computing in the Falling Walls. Do you see a pattern? And is there a pattern in your eyes?
Well, what's really striking is we are seeing these great strides in quantum computing and so much effort being poured into it and such results coming out of it. But it's clear from talks like these that we are still a long way to go, and there's still huge fundamental questions and fundamental physical problems that we need to resolve before we can realize that dream that we've had for so long about quantum computers.
Who is the next winner in the category Physical Sciences? I'm delighted to announce Samantha Joy, University of Georgia, and her project's title is Exploring Earth's Inner Space, Deep Ocean Extreme Environments. Daniel, what does the jury say about this research?
Well, you know, some are looking for life very, very far away. And then we realize just under our feet, under the sea, there is actually life we don't understand. By the way, interesting to see that this is the physical sciences, right? We're talking life and we're talking physical sciences. Should have been the life science, but yet the tools that she's using and the way she's looking at life at very deep, in very deep seas is a very interesting tool. I'm sure you should be talking about. But mostly what is really unthinkable is that life can develop under amazing pressure, under amazing salinity, in the conditions that we believe that life should not exist. Yet it exists, and it's actually also very beautiful. So we thought that this multidisciplinary approach is, you know, coming from physical science is really a very, very interesting topic.
So let's listen to the interview with Samantha.
Breaking the wall of the deep sea. Samantha Joy, University of Georgia.
The deep sea is far more than a matter of scientific curiosity. The solutions to a number of globally significant grand challenges exist in the deep ocean. Things such as discovering new antibiotics and antivirals, potentially discovering novel modes through which organisms produce energy, so bioenergy production. All of these sorts of things await discovery in the deep ocean.
And when you say you're investigating the deep ocean, what does this look like in practice? Are you sending unmanned vehicles? Are you going yourself?
I've been down to the bottom of the ocean over 100 times, and it never gets old. It's an exciting experience. There's always something new and different and unexpected.
And can you give a sense of the kind of things your work has been able to uncover so far?
We've discovered a number of different new to science microorganisms that have just incredible physiologies and a lot of unique biochemistries that potentially are of use to biotechnology. We've discovered new modes of elemental cycling and processing on Earth. We look for organisms that exist at the edges of what we consider palatable for life. So essentially organisms that are eking out an existence at the very edge of what we think is metabolically feasible.
What is the biggest hope you have for the influence and the effect that your work has?
One is obviously to advance science, to discover new molecules, physiologies that could advance the human endeavor. The other is to introduce people to this just incredible habitat.
For you, what's been the most perhaps surprising thing that you've discovered in your years of work?
We had this site that we had worked at for probably the better part of a decade, and we were going from one location to another, and I happened to sort of look out of the porthole and I catch a glimpse of what looked like filter feeding animals in a pond, a little pond of oil that was maybe a couple of meters in diameter. And they were actually quite happily living in this pool of oil. So I think the sort of the lesson there is that life adapts in ways that you don't necessarily you wouldn't necessarily think or predict. And these particular animals had, they appear to have microorganisms living with them that produce soap that keeps their gills from getting clogged. And then they have another microorganism that helps them survive. And the only reason that we found this was because I looked out the window. And that's why when I describe, doing science, I think of it as this sort of infinitely large puzzle that we really don't even know the edges of, because it's up to us to fill it in and build it out throughout our career. And if we have edges, we're doing ourselves a disservice because we're limiting our imagination.
Can you give an example of something that you've uncovered that has stretched the boundaries of our imagination?
We found a large sulfur bacteria growing in the Gulf of Mexico, a type of Thiomargarita, that actually, when it is stressed, when it's hungry, when it doesn't have energy, it goes through this process called reductive division. So the size of the cell stays the same, but it divides and it becomes what looks like a growing vertebrate embryo. So it's something that we never would have expected. I remember the day when we sort of came to this conclusion, and it was astonishing.
Adam, it seems that as a scientist, you often need a big spirit of exploration, right?
Yeah, for sure. I mean, and here, so literally, this is real exploratory work, but in some sense, it's a metaphor for all scientific research. You need to know where to drive your ship and when to look out the window.
Mm-hmm. Our next finalist is focusing again on quantum computing. I'm delighted to introduce to you Arno Rauschenbeutel, Humboldt-Universität zu Berlin. He is aiming to break the wall of quantum nanophotonics. And I'm asking the jury chair, Daniel, what is the reason for the jury to vote for this research project?
Well, we talk about computing, but as you see right now, we're using computers and we're communicating. So communication, computing without communication doesn't work. And quantum communication is another, I would say, revolution which is on its way. And what Arno's been doing here is really pushing the limit of what happened with light, which is basically the fundamental, photons we're using for communication. When you pull this light to a very, very confined space, very strange phenomena happen, new ideas emerge, and we were very, really amazed by the imaginations. It's completely unexpected effects that you could discover, which might actually have large effects on how communication will happen in the next few decades. So we thought this is really fundamental work with very large implication in the real world, and we appreciate that very, very much.
Well, so let's have a look at the video and get an idea of his work.
Breaking the wall of quantum nanophotonics. Arno Rauschenbeutel, Humboldt-University of Berlin.
So in my group, we make very thin optical fibers. They have a diameter smaller than 1/100th of a human hair, and we use them to interface atoms. That means we couple atoms to the light that propagates through these fibers. And the goal is to tame both atoms and light particles and make them usable for things like quantum communication.
And I understand that when you say you're taming atoms, you're actually often taming single atoms.
We do work with ensembles of atoms and also with single atoms. We can even see them. So when we send light through the fiber, the atoms are excited by the light and will fluoresce into free space. And using a microscope and a very sensitive camera, we can even see the atoms which are sitting on the fiber.
Now, to some people, this might seem like a bit of a random thing to somehow harness a single atom to a glass fiber. But there is actually a reason you want to do this, right?
That's right. So a single atom can be seen as a light source, but it's a special kind of light source because it emits single particles of light. And if you're able to communicate with single particles of light, then you're actually able to communicate in a fundamentally tap-proof way. So that is called quantum communication. And you would like to send the light particles to your receiver, but the best thing you can do in that case is to directly couple the light from the atom into the fiber using such an interface where the atom is directly sitting on a fiber and sending its light along the fiber.
And how much does this change what we're able to do with atoms communicating with their single light particles before?
So currently you can buy quantum communication systems. They're commercially available. Now the secret is, however, to be able not only to send photons on their way, but also, for example, to store photons and to relay them and also to process them. So having one photon interacting with the other. And in that case, atoms are a very good choice because the photon that is emitted by a given atom will be certainly interacting with another atom because both atoms are fundamentally the same. They are like God-made and there's no difference between one atom and the other. So atoms can talk to each other naturally.
Now, how hard is it actually to capture a single atom and harness it to this incredibly thin glass fiber?
So if you come to our lab, you will see a quite complex experiment. It is typically on two tables where one hosts the lasers and the other one a stainless steel vacuum chamber inside which we have nothing but a few of those atoms which we will trap and couple to our fiber. So the whole thing is really still a complex experiment, and one of the directions in which we are working and which I would like to realize also changing my affiliation and coming to Berlin is to be able to integrate these experiments into a size which is then compatible with real-life applications.
If you want to learn more about the breakthroughs we are presenting today, you have got the chance. Go and use our Q&A session, and you can talk directly to the winners. Take the chance at 3:15 p.m. German time. So I'm glad to introduce to you our next winner. And this is Michael Eremetz, Max Planck Institute für Chemie. And she wants to break the wall to room temperature superconductivity. Daniel, what is the explanation of the jury?
Well, superconductivity was discovered exactly 109 years ago. But to get to superconductivity, which allows you to transport electricity without losing, which is a huge impact, would have a huge impact on energy saving, you need to cool materials to very, very low temperature, about absolute zero, minus 270 degrees centigrade. The holy grail of physics for 109 years was to bring this temperature to room temperature. And the first one to have done that is actually Michael. Now, to be honest, it's room temperature, but very, very high pressure. But still, yet, this is an amazing achievement. And of course, the high pressure doesn't allow yet to use these kind of technologies on a daily life. But it is the first time we can observe a superconducting material at room temperature. And I think that's a real breakthrough. And so the jury thought this is really going far, far, far off.
Mm-hmm. Then let's take the chance and meet her in the video.
Breaking the wall to room temperature superconductivity. Michael Eremetz, Max Planck Institute for Chemie.
We are working in high pressure field. In high pressure field, there are two accepted so-called holy grails. One of them is room temperature superconductivity, another metallic hydrogen, which is connected because metallic hydrogen could be room temperature superconductor. Recently, we found that hydrogen become metallic together with Sasha Drazov and other collaborator in my small group, and found also 200 Kelvin in hydrogen-related compound, hydrogen sulfide.
How do you go about squashing hydrogen, and just how hard are you squashing it?
We take normal common hydrogen, cool it down, make it liquid and solid, and then squeeze more than 10 times in volume, 15 times in volume. The pressure inside of this, for comparison, is 3.6 megawatts. So we can go to pressure even higher than in the center of the Earth.
So metallic hydrogen has long been predicted as theoretically possible, but why would we actually want to create it?
Hydrogen is the simplest element, but only proton and electron, nothing more. So it's fundamental interest in what will happen with the simplest element. Another thing that, amazingly, our solar system is full with metallic hydrogen because it's the main constitution of Jupiter and Saturn. And the third goal, that there are predictions that metallic hydrogen can be superconductor, and even not usual superconductor, but high temperature, room temperature superconductor.
What would it actually allow us to do if we could have a room temperature superconductor?
This is storage for energy. So instead of capacity, we can have very big storage bank of magnets.
Could you give a sense of the hurdles you had to overcome to actually achieve this breakthrough?
It was a strong belief in scientific community that superconductivity, conventional superconductivity, cannot be high. So it's always considered like low temperature phenomenon. And the highest temperature was achieved is 39 kelvins. It's minus 200. And what we have done is really big leap from 39 Kelvin to 200 Kelvin. And so it's breakthrough not only in number, but also psychological breakthrough. And this is really important because after that, many people start to participate in this field. This field grew tremendously during 5 years. And so now we have really good chance and all basis to research ambient pressure superconductivity for future application.
And what would be your dream result from this research eventually? What would you like to see one day coming out of it?
With superconductivity or as other material, it's my dream now. It's superconductivity not at high pressure, but ambient pressure at 100 Kelvin.
And Adam, what is your estimation? What implications this research might have?
Well, it's fascinating purely from a physics and fundamental understanding perspective, but this work is also paving our way to understand what is going on with these strange high-temperature superconductors that we've now observed, and perhaps one day unlocking the door so that we could build a superconductor that works at room temperature at some kind of normal pressures and can be used from everything from nuclear fusion to the quantum computers we've been hearing about today.
Let's have a look at our next winner. I'm glad to announce Walter Leitner, RWTH Aachen Universität. And I would like to ask Daniel, what did the jury like about this research subject?
Well, first of all, it talks about a very important problem for society, which is global warming. And I guess everyone knows that one of the major or most important factor for global warming is CO2. And what Walter has been doing is developing new catalytic processes that would allow to capture CO2 from the atmosphere and transform them into something which is useful. Now, it's not the first one to think about doing that. The CO2 is a very stable molecule, which makes it very, very difficult to use in a chemical process to transform into something else. But they've developed a new process, which is a very, very curious one, very new one, very original one. And it seems to work, actually. They seem to be able to really, industrially speaking even, transforming CO2, reducing the amount of CO2 from the atmosphere into a product which we could use. So the societal importance of such a discovery is enormous. And if this could be transformed into real applications, that would be a revolution and change really the way we look at our use of energy. And of course, the major problem we're facing for the future, which is global warming.
So we are getting curious. Here comes the interview.
Breaking the wall to closed carbon cycles. Walter Leitner, RWTH Aachen University, Max Planck Institute for Chemical Energy Conversion.
The main breakthrough is that we found a way to use carbon dioxide as a raw material for very valuable chemical products. And the key to this was the development and the finding of what we in chemistry call a catalyst, which is a material that brings the two partners together, the carbon dioxide and its reactive partner, to make the final product. So the catalysis research was the core of the innovation and of the breakthrough.
Now, this might sound like a really obvious thing we'd like to do, taking this otherwise pollutant and doing something useful with it. But why is it actually a very difficult thing to do?
It's very difficult for two reasons. One is that carbon dioxide is very low in energy because it's the end product of combustion. And so we need to have it together with a partner that the two can come together and form useful products. And in addition, carbon dioxide does not want to do that. It doesn't really want to come together with the partner. So we need something that we in chemistry call a catalyst to make that liaison very stable and that the two partners come together.
And you've shown that you can actually make useful materials from carbon dioxide. What are these materials used for in the real world?
Well, polyurethanes today have a very big market. They're used, for example, in soft foams, like mattresses or cushions. They have lots of other applications. And what we have been able to show with our partners is that if we use carbon dioxide as a raw material to make such materials, actually the applications can be almost in the same way, sometimes even better than today. So there's a direct market for these products in very many applications that we have every day around us.
Of course, it's one thing to make something, it's another to show that it's actually economically feasible. Where are you in terms of actually demonstrating that this could be a feasible alternative way of making these products?
Our industrial partner, the company Covestro, has built a plant with a capacity of 5,000 tons of product per year. So that's not a full-scale plant in this field, but it's a very sizable plant that takes a lot of investment to actually build it, which clearly demonstrate that they see an economic value, which results, for example, from the fact that carbon dioxide is a relatively cheap material, so it can save money to use it. On the ecological side, the use of carbon dioxide avoids the use of the fossil raw material and leaves fossil carbon in the ground, replacing it with CO2 that we have anyway. So that also is a great benefit on that side.
What is your ultimate hope that chemistry might be able to do with carbon dioxide and with catalysts?
The ultimate goal would be to really be completely independent of fossil raw materials and of petroleum. And just like nature does it, have carbon going in cycles in our technologies that we need to make the things that make our life possible, or at least nicer on this planet.
Adam, can you tell us how would this fit into the picture of climate change? Is there a connection?
Yeah, absolutely. I mean, we know that in order to limit global warming to what the world has agreed we should limit to, we need to get to net zero emissions and get to net zero emissions as soon as possible. So ending our reliance on fossil fuels, not just in the production of electricity, but also in the manufacturing of useful products, can't happen too soon.
Mm-hmm. Okay, now let's have a look at our next winner. I'm glad to announce Tilman Pfau, University of Stuttgart. He's going to break the wall to super solid matter. Daniel, what does the jury say about this?
Well, we all know about solid, fluid, and gas, right? That's the kind of matters we're used to. But for several years, we know about another state of matter, which is called superfluid. We don't yet know exactly what we can do with it, but that state of matter allows us to have a better understanding of the interactions between the components of matter, rather than atoms, basically, and the interaction, the magnetic interactions, and so forth. And what Tilman has done is developing techniques that allows to probe into this new state of matter, which not only allows us to understand that specific state of matter, but actually the complete set of interactions between atoms in matter in general. So we very much like the experimental approach. We like the ideas, and we like the fact that using a very unique state of matter, which is rather new, allows us to understand better how matter behave in general. So for that, expansions of ideas from a very unique field, or maybe narrow field, we could even think, we can immediately get better ideas about basically all matter, and that was very impressive to us.
So let's watch the interview Adam took with him.
Breaking the wall to super solid matter. Tilman Faul, University of Stuttgart.
States of matter are around us in various forms. There are solids, liquids, fluids, and gases, very familiar to us, and even mixtures of those. So the discovery that we made is that there can be a new state of matter, which is not just a classical mixture of two states, but a quantum mechanical superposition of the two, which is a big difference. This is called a supersolid, which is at the same time crystalline and solid, and superfluid, which is a fluid without any friction. So this state of matter is elusive since 60, 70 years. It's discussed a lot in the physics communities, never was observed in that clear fashion. And we were able last year to prove that this state of matter exists in our lab.
Now, this kind of weird quantum behavior is something normally associated with, say, single particles like electrons or photons, or maybe sometimes entire atoms. But you're looking at a state of matter. How big an object are we talking about that you have in this quantum superposition of being two things at once?
In our lab, what we prepare is typically a sample that has about 20,000 atoms, which is small on the scale of a normal piece of matter, but it's large compared to what has previously been brought in superposition states.
So now that you've actually created this state of matter, what kind of things can you learn about it?
There are two different sound waves in the material that we discovered and observed. Waves are propagating between us when we are talking through air. They are also propagating as waves through fluids or through solids. But they have very different speeds depending on what kind of substance, what kind of material it is. But if you have a super solid, which consists of these two kinds of materials, maybe it's intuitive also to say or to expect that there should be two kinds of waves that are propagating through the material. So if you knock on this super solid, then two waves will start to propagate. One is arriving faster and the other one is arriving later. So if you listen on the other side of the material, then you would hear two knocks basically that are delayed with respect to each other.
Now, why do we want to study and create states of matter like this super solid in the first place? Is it purely to understand our universe better, or could there also be some kind of application of this kind of research?
First of all, I should say this is really curiosity-driven basic research. We are just curious, what kind of states of matter are possible in the quantum world. And it turns out there is a variety of states of matter that we thought would never be possible with our classical understanding. So most of the excitement at this point is about this discovery that, you see a piece of matter in a state that nobody has ever seen before.
Being a physicist, Adam, what are you taking away from this?
Well, I think as any physicist, when I first learned about quantum physics, my mind was blown. But you can reassure yourself that the weirdness of quantum physics is only the way it is because it concerns single atoms or single electrons. But then when you hear about an entire piece of matter behaving in this absolutely bizarre quantum way, I mean, it's quite disconcerting in a way.
Okay, let's continue with our next winner. I'm glad to announce Frank Flechtner, Helmholtz Center, Potsdam. He wants to break the wall of monitoring global water resources. And Daniel has got the explanation of the jury.
So we talked already about climate change and CO2. And as you said, we need to monitor. As long as we change the climate, we need to monitor it. And monitoring is not only temperature, but also the rise of water, iceberg falling apart, and sea level change and so forth. And what this group has been doing is quite amazing, because using satellite technologies, which is actually flying very far off Earth, they've been able to measure the change of sea levels to a precision which is unthinkable, or the breakout of iceberg in a way which, you have to be there to see it, but in fact you don't, because you can see it from space, not just by seeing it, not just by watching it, but using satellites that use very, very sophisticated physical instruments to measure these kind of things. And we thought that the mixture of environmental watching, satellite technologies, very precise detectors, and of course global warming watching is a very interesting, again, multidisciplinary work, which really, to be honest with you, blew our mind. That was not less than that.
So we should learn more about this potential breakthrough.
Breaking the wall of monitoring global water resources. Frank Fletchner, Helmholtz Center, Potsdam. GFZ, German Research Center for Geosciences.
The challenge of my work is the monitoring of the continuous redistribution of water masses in system Earth, which are affecting sea level rise, ice melting, groundwater depletion, or changes of deep ocean currents.
How actually do you go about measuring the distribution of ice and liquid water on Earth?
So we have a twin satellite pair, which we call GRACE, which is for Gravity Recovery and Climate Experiment. And these two satellites fly in about 500 kilometer altitude and 220 kilometer separation. And the gravity changes due to the different mass distribution on the Earth's surface, for example, by melting ice, cause tiny changes in the separation of the satellites. And that is our prime measurement, which we use to collect monthly maps of mass transport models.
And could you give a sense of what we already knew before GRACE, how much we already knew about ice distribution and also groundwater?
It was impossible to say on a global scale, on a monthly time scale, where everywhere groundwater is depleted, or we didn't know if Greenland loses ice and how much, if yes, how much it loses. And now we have numbers for that over a time period of 20 years and get confidence that this is really real. Yeah.
What can GRACE tell us about the impact of these changes, both today and in the future?
It is believed in science community that you need, let's say, 30 years to give reliable statistics if climate change is happening or not. But we can distinguish already today how much from sea level rise is affected by mass inflow, by melting ice, and how much is due to thermal expansion. So that is somehow new.
So now that we actually have this description of what's happening thanks to GRACE, well, what do we do about that? Who would you like to know about it, and what would you like to be done about what we've learned?
Yeah, I think our job is to, let's say, perform the observation, to monitor the mass change, to build reliable statistics on all these effects. But I would wish that the politicians in countries which are responsible for climate change, like the US or Brazil or let's say China, India, and so on, that they really get aware on what we have observed and how it is affecting our future.
Adam, what impact do you see by this research?
Well, it's amazing work, and the technique itself is just beautiful, remote sensing what's happening here on Earth using these satellites. But ultimately, what it's showing us is what we're doing to the planet, and it's not painting a very happy picture. We're seeing that we're destined to more and more sea level rise unless we can get emissions in check.
Mm-hmm. So, ladies and gentlemen, 9 winners we already met in this category. 1 is left, and I'm delighted to announce our last winner in the category Physical Sciences. And this is Pete O. Schmidt, Physikalisch-Technische Bundesanstalt. He's aiming for breaking the wall of laser spectroscopy. And Daniel, what is the reason of the jury?
Well, clocks are everywhere, right? We depend on time, and we're used to the, to the feeling of time. And we use actually clocks all the time, not only on our wrist, but in fact, even here right now, we're using clocks to synchronize our video and our signals. Or even more, when you travel the city of Berlin, where I guess you're located, you need the global positional system, the GPS. And most people don't know, but your GPS system use large number of atomic clocks that are located in satellites orbiting Earth. Each of these satellites has 2 atomic clocks. And what Peter has been doing is trying to increase the already incredible precision of this clock using very sophisticated tools and new ideas. And in his last experiment, succeed to improve this by order of magnitudes. Now, people would say, who cares about having time which is so precise that anyway, we cannot even count it, but that's not true. Just as the global position system demonstrated, you can use these kind of things for many applications, and we will need them for a lot of sensors that actually even the previous experiment I'm pretty sure is using. So this is quite a very fundamental discovery. It has also implication in fundamental physics because it will allow us to measure better fundamental constants, but also might end up having very strong applications. So we were really, again, blown away by the fundamental part of the work, but also the future applications and implications of being able to measure time so precisely.
So let's watch the video and learn more about this.
Breaking the wall of laser spectroscopy. Pete O. Schmidt, Physikalisch-Technische Bundesanstalt.
Highly charged atoms are among the most abundant species in the entire universe and have been investigated in the past. And in our research, we have improved the resolution by 9 orders of magnitude by employing coherent laser investigation of the properties of these atoms that can be used in applications ranging from optical atomic clocks all the way to studies of plasma physics in the universe.
Now, given that these atoms are such a common part of our universe, why are they so hard to get a good look at?
These species typically live in plasmas. Yeah, this is essentially they're generated through electron bombardment, which is a very harsh and very violent process involving huge energies. With these huge energies comes what we call Doppler broadening. So the lines become very broad because of the high temperature of the ions of these charged atoms in the plasma. And what we've managed to do is to actually cool these charged atoms down almost to the lowest possible state, corresponding to a few millionths of a Kelvin above absolute zero.
And your approach has allowed you to study these atoms in unprecedented detail. Well, how unprecedented are we talking? What added detail are you able to get?
Currently, we've managed to improve the spectroscopic resolution by 9 orders of magnitude in essentially our first go by using a completely new technique that has been developed in the context of quantum information processing with charged atoms, and we're applying these techniques to perform spectroscopy on these highly charged atoms.
Do we just want to study these highly charged atoms so we can better understand them, or can they actually teach us something about the wider universe beyond themselves?
These highly charged ions have actually been identified as being the most sensitive atomic species, for example, to test certain aspects of fundamental physics. And if we now compare properties investigated by a laser of these highly charged ions to neutral atoms or singly charged atoms, then we can put bounds on, for example, variations of the strength of the electromagnetic interaction. And that gives us a possible glimpse into dark matter, for example.
Now, could these highly charged atoms have any applications in the more mundane, everyday world beyond the world of experimental physics?
What we're trying to do here is to build excellent clocks, excellent optical clocks. Best clocks currently operate at a fractional uncertainty of about 10 to the minus 18 and have widespread applications starting from navigation to synchronization of networks, measuring height differences over large distances. And with our highly charged ion clocks or highly charged atom clocks, we of course can contribute to this race who has the best optical clock. Yeah, that's also one of the goals that we want to investigate, how far we can push the accuracy of these new species.
So that was the winner's session in the category Physical Sciences. Congratulations to all our winners. Good luck for your work, your projects and everything. And good luck for the grand final on Monday, November 9th. We will celebrate the best of the best. We will get the breakthroughs of the year 2020 through all categories. So for today, I would like to thank very much Daniel Seifmann, the jury chair of this session. It was a great pleasure talking to you. Thanks a lot, Daniel, and have a nice day. And Adam, thank you as well. It was great talking to you. Thank you for giving us insights. Stay with us since we will continue now with our next winner session. And this will be the category Science Startups. And you will meet the next 10 winners in a minute. Hello, here we are again at the winner sessions with the Falling Walls Breakthroughs of the Year 2020. My name is Astrid Frohloff. I'm a moderator and I will guide you through this session. Over the past months, more than 900 nominees from over 100 countries have made their journey to become the Science Breakthroughs of the Year in their respective category. And today in this session, the top 10 winners in this category, Science Startups, will present their breakthroughs. And here in the studio, I'm joined by Dr. Adam Levy, co-host. He's a physicist and a science journalist, and we will hear from you later, Adam. Glad to have you here. And I'm also very pleased to welcome online today Frank Kalkbrenner. He's a jury member of this category. Great to have you joining us, Frank. As you probably know, we have got 10 categories, all in all. Each category is accompanied by a very prominent jury. Each member of the jury is a distinguished expert in his field, and we are very thankful for their help and their contributions. So, Frank, you are global head of Boehringer Ingelheim Venture Fund, physician by training. Let me ask you, if I had a few millions euro in my bag and wanted to invest in a science-based on startup now, could you give me a good advice?
Of course, the first thing I would come up is biological science, yeah, since this is really my home turf. And in biomedicine, we have a very few very exciting developments. We have a lot of progress in treatment of tumors, especially immuno-oncology is very interesting. We have a lot of development ongoing in regenerative medicine, which will become very prominent, especially in our aging population, where we'll see a lot of patients needing this therapy. We also have a lot of development in digital health. Yeah, digitalization of the society is anyhow very important, and this would be a separate topic for me to recommend to you in your investment portfolio. But digital health per se is very interesting. We will have a lot of remote interaction between the physician and the patient. We will have a lot of remote diagnostic tools ongoing. So this is very interesting. But don't skip the area of infectious disease. At the moment, infectious disease is not well served by research, but infectious disease will become very prominent in the future. We experience this every day in the COVID-19 pandemic situation. Infectious disease is very important. But there are also other areas of science I personally would invest in, and a few of them you already addressed in the former section. This is climate change. Climate change is the one important issue for mankind. Yeah, and and there are many technologies. I think the human beings are very bad in avoiding things. Yeah, we are very bad in avoiding driving car. We are very bad in avoiding eating meat. We are very bad in avoiding heating our houses, yeah, or heating our houses in a different way. But we are very good in identifying new technologies, how we can replace the meat from livestock with fish protein. That's something you see also today in our session. But there are also a lot of technologies around to generate renewable energy and to store renewable energy. This is really a technology which will be very important for our future, and also how we can reduce the CO2. And we heard already a lot about this in the last session, and we will hear something about this in this session. Also material science. We have a lot of development, very exciting technologies in material science, and you will hear something about this also in our session.
Right.
These are the main topics I would invest in: climate change, material science, digitalization, and the biomedicine improvements.
Okay, thanks for your advice. Thanks for the moment. Adam, let me ask you, what inspired you most in this category?
Well, it's such a broad category. Of course, we've heard how many different inspiring topics there are here, but what was common across all of them is this passion, this enthusiasm, this, I suppose, tendency not to avoid these difficult questions and instead tackle them really head on.
Okay, so who are our top 10 winners in this category? Let me announce the first winner. This is Dr. Evelina Vegezieux. She wants to break the wall to next generation biologics. And I'm asking Frank, what convinced the jury most about this project?
The technology that they use is really a new trend in biomedicine that is using engineered bacterial as a new delivery technologies. We have seen in the past 20 years viral vector systems, liposomes, nanoparticles, but now the using bacteria is going back a little bit in complexity. That means also back in cost of goods, and is easy to produce. They are very cheap to produce, are very stable bacterial. And on the other hand, the indication this company is addressing wound healing and inflammatory bowel disease are very important. Wound healing is an increasing problem in the population, especially in diabetic people, but also in elderly people. And inflammatory bowel disease is a huge indication. So the combination of easy technology with medical need and two large indications that convinced the jury.
Okay, let's get an idea. Here is a video.
Breaking the wall to next-generation biologics. Evelina Vogegoe, Ilia Pharma.
Next generation biologics is advanced therapy. We've been able to use a type of proteins that are very unstable and have a short half-life, and they affect immune cells to behave in certain ways. And we're utilizing this to medical indications at the moment, healing wounds in the skin, but also in the intestine, which is relevant, for example, in inflammatory bowel disease or any other type of intestinal injury. How we were able to use as therapeutic proteins is that we built a technology platform using lactic acid bacteria, normal probiotics, but we introduced a genetic modification in them so that the bacteria in turn produce the human protein. We trick the body into thinking the wounds are larger than they really are.
What stage are you at now, getting this out of the lab and into a position where it can actually help patients recover from wounds?
Yeah, so we developed a technology platform, which is a very important first step. It took about 2 years to build this library of bacteria, different bacteria. And we just now, 6 years later, received the first wide patents for the whole library in any indication. We decided to take one project as fast as possible to clinical validation. And then we started with skin wounds. And we have now completed a first-in-human trial in 36 healthy volunteers with this. And this is part of an EU-funded project called WILIAS, Wound Healing Ilia Style. And it's a very extensive first study, but generating all this data also plays into other indications in the future. And we also received a new EU funding for this as a direct continuation. And we are now planning a phase 2 trial in chronic wounds in people with diabetes, and we expect the first patient to be treated in Q2 next year.
Just how big an impact do you hope this could one day have on the lives of patients?
We really think that they deserve more pharmaceutical treatments and there should be more treatment options available. And some of them actually, there's no recording of even how long they've had a large open wound. And even shortening the time to healing with some weeks would make a huge impact for them. And also acquiring a wound infection is a very serious clinical problem. And if you get a wound infection, there is a high probability of this leading to limb amputation. And the 5-year mortality following one of these events is higher than in most of cancers. And for patients with inflammatory bowel disease, it could be very limiting to their daily life, where some patients need to go to the bathroom about 40 times a day. And this is not only pain, but also disabling for their lives.
A high-tech company from Germany is our next winner. The Helio Heat company, Dr. Wei Wei. It's about breaking the wall of fossil fuels. Frank, how did the jury decide about this project?
We already talked about the storage of renewable energy. This is a major problem. And this group attacked this by storage the renewable energy in heat, not to generate electricity out of this. They are heating up small ceramic particles and use the heat to transfer to factory and using for production. And this idea is something which convinced the jury.
Mm-hmm. So let's watch the video and learn more about it.
Breaking the wall of fossil fuels. Wei Wu, Helio Heat.
Thomas Edison once said, "I'd put my money on the sun and solar energy. What a source of power. I hope we don't have to wait until oil and coal run out before we tackle that. We are right on tackling that immense source of power from the sun. And with our technology, it is possible to generate renewable heat or electricity around the clock, as flexible and as secure as the fossil fuel plants. But without CO2 emissions. So we believe that with our technology, we can not only break the wall of fossil fuels and contribute to the fight against climate change, but also break the wall of cheap and sustainable energy for everyone, where energy is not only limited to wealthy industrial nations on this planet. So, well, yes, that's our breakthrough.
Can you describe how you're actually tackling this hurdle and finding a new way to use the sun's energy?
Yes, so we developed centrifugal particle receiver, and this receiver sits on top of a tower on a concentrating solar power plant. So this concentrating solar power plant basically consists of a field with mirrors, and they're reflecting the sun to one single point, and that's sitting on top of a tower, which is like in between this field. Basically, the receiver collects all the solar radiation coming from the mirrors.
A huge challenge for renewable energy is producing certain industrial materials which require, conventionally, the burning of fossil fuels to create very high temperatures. Could this be used for these kinds of applications?
Yes, definitely. So that's actually our main target market, that to really tackle these high energy intensive industries like the steel industry or the cement industry, where they need temperatures up to 1,000 degrees and above of that. And with our heat, what we generate with the power plant and the particles, we can tackle that. And right now it's not really economic to use electricity for that. So it's much better to just directly have the heat generated. And that's what we're gonna do.
What will it take to get this out of the development stage and actually out there producing energy and making electricity, making products?
Yeah, so right now we have like a really first pre-commercial project where we're gonna build the whole plant, and we have already an end user for the energy, which is Barilla, the most famous pasta manufacturer in the world. We're gonna build a whole plant next to their pasta site, and then we're gonna use this energy produced, and Barilla will use it to dry their pasta, actually. So that's our first step into commercialization, of course. And after this project, we can build on that and say, look, we have a running plant which can generate energy for pasta production, for example, right? So come up with the next applications for us. We have a working system.
Well, Adam, your focus as a physicist lies on climate change. What impact do you see for this project?
Well, we've seen over the last few years huge strides in solar and wind, both in terms of efficiency, but also in terms of cost. But there's still questions of how we can create these large-scale industrial products, questions of how we can power our homes when the sun isn't shining, when the wind's not blowing. And so work like this really starts to fill those gaps in our energy future.
Let's continue with our winners, and I'm glad to announce the next one. It's Atlant 3D Nanosystems in the category Science Startups. It's about breaking the wall to micro and nano fabrication. So, Frank, what makes the work of this startup so special for the jury?
This company developed a new technology to 3D print on a micro and nano level. And this is, of course, per se, this is also a technology to reduce the production time and to enable production of prototype. But what was really interesting, what we discussed here, is that the time to come to a prototype in this way with 3D printing is much shortened. That means that we get more prototypes in the same time. And what we see here is the kind of science enabling technology, because you can make more prototypes, you can just try a little bit more.
Okay, let's watch the video and get more information about this.
Breaking the wall to micro and nano fabrication. Maxim Plakotniuk, Atlant 3D Nanosystems.
Our breakthrough innovation is the nanofabricator. It's a molecular assembly machine that can and will enable rapid prototyping manufacturing of microelectronic and micro nano devices for various applications, from biomedical devices for detecting cancer or growing stem cells to microsensor for IoT, smart glasses, the technology that can enable much cheaper batteries, solar cell, and much more unforeseen micro technologies. With our technology, we can make a paradigm shift for our civilization and make possible advanced manufacturing technologies and shift to nanofabricators and smart factories on Earth and beyond.
Just how different is this way of making these nano materials from what we have to do previously?
In other words, what we invented and now bring into the society, to industry and academia, is we made atomically precise 3D printer, in other words. So before, even still now, to make some simple sensor micro device, one needs to work in the clean room and engage a lot of people, a lot of experts, and a lot of machines. And with our technology, with our equipment, the nanofabricator, one can make sensor like a 3D printer on many different and complex surfaces within just uploading a digital file, a CAD file, and submitting for printing. And then in the end, you get the device ready to test or ready to perform.
What stage are you at with development? Do you already have a working device, or are you selling them today?
Yes, we have a working prototype. Now we are building industrial prototype of the system. We are not ready to sell the machine to the market because it takes time. It is a pretty complicated technology. But we testing our machine already with the customers by developing at this moment more simple devices, and our target is to start developing much more complicated devices and also sales of the equipment later on to the customers who want to scale from prototype to manufacturing of the solutions. Yes.
But how difficult has it been to develop the nanofabricator?
Yes, it's a highly interdisciplinary invention, and we brought the brightest minds of chemists, microtechnology, software, hardware developers, engineers, innovators together in order to enable such innovation. I would say we made a pretty dynamic path in the development, and we only use about 3 years from idea stage to the working industrial prototype. And I would say this is because the people that were engaged were so motivated to make it, and they are still motivated. This is the team that Atlant is leading. It's not just the Atlant team, it's a team of scientists from across the Europe, and now it's going outside of Europe as well.
If you want to dive a bit deeper, check out our Q&A session. You have the chance to talk directly to our winners, either in small groups or one-on-one talks, so don't miss that chance. Let's see who is our next winner. I'm delighted to announce Andreas Schmidt of Proteona. He is breaking the wall of cancer one cell at a time. Frank, what convinced the jury about this work?
You know, the main problem in the current tumor therapy is that the tumor quite often relapse even in a short time. And the reason for this is that the tumor is not really uniform, only the conglomerate from one cell. It's a conglomerate of different various cells, yeah. And what's very important is to find out which cells are involved. Currently, you try one therapy, you fail after a few months, you try the next one, and so on. Here we have a method to study the tumor in the heterogeneity and to find out which cells are involved, and to have a combination therapy targeting all the different tumors. This is very essential, and this convinced our jury.
So we're excited to see the interview.
Breaking the wall of cancer, one cell at a time. Andreas Schmidt, Proteona.
Cancer is a disease like no other. From the people watching this video, about every 1 in 5 of us will experience cancer. So why do we fail to treat cancer so often? Because tumors are very heterogeneous. They're very diverse. There are lots of different clones contributing to it. And that's exactly what we are addressing with Proteona's technology. We are a single-cell multi-omics company. That means in a sample of a patient, we analyze 10,000 individual cells. And in each cell, there are 3,000 mRNAs, 300 mutations, 70 proteins, 200 known therapies. And then we take it one step further and use artificial intelligence to create insights that change the treatment of patients. Single-cell multi-omics will change how we find treatments for cancer patients and how we design oncology pharma trials for the future.
Can you explain just how different your approach is to how we conventionally treat cancer today?
Well, if you look at a tumor sample today, you typically put everything into, well, let's call it a mixer. You measure it, and then you do your measurements on this mixture. And of course, you're missing that there might be very, very different clones of very different tumor cells in it. And that then creates the problem. You're missing some tumor cells that might actually become more aggressive, while you can attack others in a pretty good way.
Is this something that is still in the lab, or are you already using your approach of single-cell analysis to patients?
Well, 2 years ago, we were a research platform. We were truly in the lab. And then we did a very, very detailed analysis of our first patient. We sent it to clinicians, and we fell from our chair when we heard that that was actually insight that was used to treat the first patient. And since then, things changed. All of a sudden, we are a precision medicine company, and insights from our single-cell analysis can actually benefit patients today.
For you, what's stopping this now becoming a really widespread way of treating cancer?
Well, what we are doing is revolutionary, complex, expensive, and a process that will take still a bit actually to get to everybody. So we are working with multiple partners around the globe. We characterize more and more patients, and we hope that one day that will be the routine way of addressing cancer, but that still requires some scale up.
Can you give a sense of just how cutting edge the techniques you're applying here are?
Well, I mean, just look at Nature. They selected the method of the year for 2019. That was single-cell multi-omics. And later we got an award as one of the most innovative spin-offs. And I think that very much shows off how cutting edge that is. Like probably for the last 2 years, it's possible to combine genomics and proteomics on a single-cell level and then put this information together. And we take it one step further to integrate data from different omics areas, from RNA, from DNA, from proteins, which requires artificial intelligence and is brand new.
Let's continue with our next winner. I am glad to announce Nanowired, Olaf Birlem. And this project is focusing on special technical aspects of material joining. Frank, what is the explanation of the jury?
So far, we use physical methods, chemical methods, heating to bring parts together. Yeah, and this physical chemical method also changed the material of the parts you want to bring together. What these inventors found out is that there are different methods to put things together at room temperature. Yeah, and they call this clad welding or nanowiring, clad sintering. And what is very essential, if you use this in microelectronic, you can put things together without modifying this, without modifying the characteristic of the material. And this will have a big impact in the industry, especially in microelectronics.
Mm-hmm. Let's watch the video and learn more.
Breaking the wall to material joining. Olaf Böhlem, Nanowired.
Our breakthrough innovation is that we are the only company who has developed a dry, room temperature-based joining method for a copper-copper joining like a metallic Velcro. And with this, we shrink big joinings down to 4 micron, and you can use the same method for all type of joinings.
So why is this approach, a kind of metallic Velcro, preferable to conventional ways of joining 2 bits of metal together?
Today, we use soldering. This is a heat-based process with a liquid. And so you've got capillary force-treated shortcuts, and the heat destroys the electronics. And with our room temperature dry process, you get a low current or a low resistance and a high temperature throughput. So it's a breakthrough for all electronics to shrink the things tiny and more tiny.
What kind of applications do you have in mind specifically?
Today, we completely focus on the electronic and electric markets, and they are the e-mobility, then everything with IoT, so Industry 4.0, and the complete converted technologies. So if you want to make autonomous driving for cars, you use our technology to let the microcontroller run in the car and bring the energy out of, so that the thinking runs the best way.
It sounds definitely like a very cool way of joining 2 bits of metal together, but how strong actually is it?
So just to compare with existing technologies, I speak in some numbers. So a normal gluing technology, if you glue something together, you've got something like 12 megapascal, but just only remember 12. If we make our joining, we've got 60 megapascal, and if you use additional force, you can rise up to 100. So we have sometimes 10 more time the force resistance than the existing technologies.
What stage are you at today with both development and production?
Today, we industrialize production. So we've got more than 50 international companies we play with, something like Honda, Toyota, VW, on the one side, on semiconductor, or Intel, some big semiconductor players. And with these companies, we industrialize the process. And today, like with this machine, we are able to grow fully automatically nanowires on individual surface. And end of this year, we have finalized an industrialized nanowiring production machine. And last year, we had a turnover of 1.2 million euros.
What's your hope for the future, for how widespread this could become as a technology?
So you know Intel Inside, and the future is nanowired inside. So all electronics and all mechanic instruments will have our technology as the breakthrough technology for the next scale factor.
If you would like to get connected with other Falling Walls participants, you have the chance. It's easy done. Use our Brain Dates platform. It's a great network tool. You'll find it on our webpage. So our next winner is focusing on the issue of battery technologies. We are delighted to announce Off-Grid Energy Labs' Tejas Kusurkar, who is aiming for breaking the wall of toxic batteries. So Frank, what is the reason for the jury to vote for this project?
We know that we have in all of our life, daily life around batteries, yeah, and we have electric cars, and this trend will go on. And there are so many battery companies who work for more storage capacity, a longer way you can go with your electric car, and so on. But the problem, what many of these companies do not address in the first place, is to use non-toxic disposable material. And this was one of the topics for this company, that they use 100% sustainable and non-toxic material, and they came up with the solution of a zinc shell battery, and the environment-friendly production. That's what drove the decision of the jury.
So we are excited to meet the winner. Here's a video.
Breaking the wall of toxic batteries. Tejas Kusurkar, Off-Grid Energy Labs.
So we have built an efficient battery using sustainable and commonly available raw materials. We call it zinc gel battery. There are three breakthrough innovations in this battery. First one is into electrolyte, which does not use any water or other organic solvent. That's why it is really very safe and it will never evaporate. The second innovation is into use of sustainable materials. Some of them are based out of carbon and other material is zinc. And third part is into design. We have designed the battery in such a way that existing battery makers can make this battery without any change in their infrastructure. So this battery is robust, easy to manufacture, and has a longer life. That's why it can offer lowest cost for energy storage, for stationary and mobility applications.
In what kind of situations would this be more useful than conventional, for example, lithium-ion batteries?
There are two problems with lithium-ion battery. First is lithium is not mined everywhere. So the raw material is really very scarce, and that's where we can play an important role. Second is that there are performance limitations in lithium, such as rate capability, temperature stability, and that's where our batteries can perform really very. Let's take an example. If we talk about grid balancing, we need batteries that has high rate capabilities, and zinc gel can offer high charging speeds without affecting any life, and that's really very special about it.
What stage are you actually at today? Is this something that's already out of the lab?
So at present, we would say we are at TRL 5 with respect to NASA standards, which means we have done all testings in internal and external labs. And today we are building high fidelity prototypes that would go actually on field to try.
Now, you're not the only organization developing zinc-based batteries. How does what you've designed compare to other zinc-based batteries around the world?
Correct. So there are zinc is one of the oldest chemistries, right? It was used 200 years ago. But there are two major categories that are being used today. First is zinc air, and other is zinc flow batteries. Now, with respect to zinc air, we have higher energy efficiencies. And if you talk about zinc flow batteries, we are much cost efficient than those batteries. And that's where, and with respect to both, our manufacturing is really very easy.
Why is building better batteries so important today in 2020?
Today, we are generating more and more renewable energy. At the same time, we are shifting towards electric vehicles. And both needs energy storage, because renewable energy is not reliable and continuous as regular conventional sources. And electric vehicles need better batteries. So everything boils down to batteries. And therefore, demand for batteries is going to be 10 times it is today. And those batteries have to be sustainable.
Adam, tell us what role sustainability plays in general for projects, for startups?
Well, I think, Astrid, we see really, in many ways across this category, that developments have to take sustainability into account. And it's not just about tackling solutions, it's about tackling them in a way that has sustainability at the heart.
Mm-hmm. Yeah, and we learn more about it, I think. Let's continue with our finalists. Who's the next one? FiberCoat is a company that wants to break the wall to composites, new materials, and I'm glad to announce Robert Brühl. So I'm asking the jury, what convinced the jury most, Frank?
Glass fiber material will replace steel, aluminium, especially in cars, but also in other places, just to reduce the weight, especially in cars. With weight reduction, you can also reduce the usage of the car. But here with FiberCoat, we have a company, or we have a group of young enthusiasts who developed a process which is only a one-step process, which reduces the cost significantly, which reduces the time significantly, and this way make fiber coats more more cost-effective, and can more achievable for the production, and this is the main reason convincing us.
Mm-hmm. So let's meet the winner. Here comes a video.
Breaking the wall to composites. Robert Brühl, FiberCoat.
At FiberCoat, we break the wall to composites, making these high-performance materials affordable to anyone. So usually the composite production chain is very long and complex, and we integrate most of it into one single step running at 1,000 meters per minute. The producing material has a high quality, very cheap in comparison to the state-of-the-art, and runs a lot quicker through the production steps, achieving a material that then can be used in a wide range of applications. And we are convinced that by innovating in the basic building blocks of our economy, the material sciences, we can have an impact on our community and our economy, making it more sustainable and affordable for the future.
What types of things are composites used for today?
Composites are used for high-performance applications like airplanes, sports cars, and such. So because of their high price, they're usually only used in those kinds of things.
Can you give a sense of just how much work it's taken to develop this and how big your team is?
Yeah, so this development started actually 2014, where we had the first idea to produce something like this. They remember that all of our supervisors at the university said it's impossible. But we did it anyway. And then 2 years ago, Richard, Alex, and myself, the three founders of FiberCoat, came together and said, okay, we're going to take this technology and get it in the industry ourselves, because the others, they just won't do it. So in the course of these 2 years, we then developed a system which is actually feasible to run at industrial scale. The three of us, with an armada of students, I think we had times where we had 20 or 25 students working on the project. And today we are looking to expand our team to 7 fully employed people, plus currently 12 students working on this topic.
How difficult will it be to take what you've designed and integrate it into the construction processes that already exist for composites?
Yeah, so this is actually very easy with our material, because you can use the existing machinery and parts. The only thing is that we save some of the process chains, so some of the machines will become obsolete, but in order to process it to finished parts, you can use what's there, so you don't need any new machinery, making it very easy.
What stage of the development process are you at today?
We finished the lab stage, and we also have a pilot line running, producing 400 filaments coated with polymer. This is the smallest size of industrial scale, and we aim to have the big scale of an industry by the middle of next year, starting to sell our material into the market.
What kinds of new applications for composites are you hoping this new production method might unlock?
I'm hoping that we can make things that are there cheaper, so that more people can afford those high performance things, and we can enhance those applications that are cheap and in everyday's life, so small cars, or actually toys for children, consumer goods like bicycles, making them affordable to much wider range of people so that more people can profit from those kinds of things.
Who else is on our top 10 winners list? The next winner is Spectroplast, Manuel Schaffner, a company focusing on silicone manufacturing. What was the reason for the jury to vote for this winner, Frank?
Silicone as a material is widely used in medical application. Yeah, many prosthetic parts, many implants are based on silicone. But on the other hand, the production of silicone implants is quite expensive, takes a lot of time, and that's why a surgeon has only the choice between, let's say, 3, 4, 5 different sizes of implants. This company now developed technology for D3 printing of silicone, and this will enable then the technology to go for personalized, individualized, individual fitting of implants and prosthetic, and this is a huge advantage for the patient.
Mm-hmm. So we're curious to listen to the interview.
Breaking the wall of silicone manufacturing. Manuel Schaffner, Spectroplast AG.
We are the first company to have developed pure silicone 3D printing, and this has main implications for technical products, but then also life-enhancing and life-saving medical and healthcare products.
So how is this different from how silicone products are made conventionally?
Yeah, that's a really good question. So conventionally, silicone products are made by injection molding. That's a mass manufacturing technology, basically, that needs heavy tooling, heavy machinery, and also molds, as the name already says. And this is actually quite a limiting factor in the sense of personalized products that really need to be tailored specifically to a patient or a customer in that sense. And this is not accessible today by conventional way of manufacturing silicone. And 3D printing is really the first door-opening technology in that regard to enable customized, personalized products made out of silicone that will also have a positive impact on society regarding medical applications.
It sounds maybe like quite an intuitive thing to want to do, to 3D print silicon, but why is it a challenging thing to do? How did you set it up?
Silicone itself, basically, it kind of works like baking. You need to mix two different components, then you need to push them in a mold, heat them up, and thus far 3D printing has mainly dependent on light systems. So you use light lasers basically to solidify the material spatially where needed, and the big breakthrough was basically to enable the same characteristics in silicone also to make them light sensitive, and with them also make them accessible to 3D printing.
And where is this work today? Are you still at the proof of concept stage, or are you actually at the point where customers could maybe buy one of these 3D printers?
We are just in between. So we are far beyond just development or prototyping stages. We have established a production site where we basically have several printers running at the moment, and we act as a manufacturer of these silicone parts. So right now we have the technology in-house, but we are producing these parts since, for the last 2 years, I would say.
Now, is the dream that this would replace our conventional ways of making silicon products, or would it really be for specific types of silicon products?
We don't believe it's going to completely, change the way silicone products are made, but it's definitely a complementary technology to what I mentioned before with injection molding, mostly for smaller series, so from basically a single part up to 1,000, 10,000 parts per year, and then everything that needs to be customized is definitely where silicone additive manufacturing becomes invaluable.
Again, if you would like to learn more about our winners and their future breakthroughs, don't miss our Q&A session. It starts right after this show, and you can talk directly to the winners. Our next startup is also focusing on new materials. I'm delighted to announce startup Made of Air, Alison Dring, and they want to break the wall to carbon-negative materials. Frank, what was so fascinating for the jury about this?
We talked at the beginning of this session about the importance of climate change, yeah, and climate change is caused by the increase in CO2 in the atmosphere. And this company developed a technology where they can produce a granula which locks CO2 into these granula, yeah, and this granula can then be used to generate different products and like every other plastic material. And what is very important is here that we can take the CO2 out of the atmosphere and leave the CO2 from the fossil energy in the ground. And this, in the long term, will reduce the CO2 in our atmosphere. And that's very important, as we discussed at the beginning.
Yes, let's learn more about this potential breakthrough. Here comes the video.
Breaking the wall to carbon-negative material. Alison Dring, Made of Air.
So at Made of Air, we're developing a carbon-negative material. And we're considering the materials that make up the products that are all around us in our environment. These materials typically come from fossil resources and have very high CO2 emissions. It's clear that manufacturing needs to cut the cord from fossil resources. But when we consider our coming demand, we ask where the materials are going to come from. So at Made of Air, we look at climate change in a very different way. We see it as an oversupply of carbon in the atmosphere, and that is actually a material problem. So our question is, what if we can take this biggest challenge, this existential threat, and make it into our biggest resource? So Made of Air is producing a durable thermoplastic that stores carbon in products, and it enables manufactured goods to become carbon sinks. So we're selling this by the ton into manufacturers, into industry, such as facades, furniture, automotive, and we're currently engaged with 7 different consumer brands. We have 3 active pilots, and this company really believes that the future of materials is carbon storage.
Now, what actually is it about your material that makes it carbon negative, absorbing carbon dioxide overall?
Sure. Well, the material itself is carbon negative because it starts with the origin material, which is wood waste. And this is a waste stream that, like any biological material, has absorbed CO2 in its lifetime. What isn't commonly known is that when the plant starts to decay, the CO2 is going back into the atmosphere. And what we're doing at Made of Air is interrupting that natural cycle and converting that wood waste into biochar, which permanently locks the CO2 into a material that does not go back into the atmosphere. And then we take that material and we put it through a series of refining steps, and what we get is a thermoplastic granule that's ready for use.
How also does it compare with the fossil fuel-based products it would replace in terms of both cost and how well you could scale production?
Sure. Well, this is a material that can compete with the bioplastics market. It's at price parity or cheaper. It's highly scalable into different industries. We can currently produce with the supply chain in Germany. Our future target for our first facility will be 2,000 tons a year, and scaling up from there within 10,000 tons within the next few years.
Just how big a difference can materials like these make in our fight against climate change?
Materials actually have a huge potential to have impact, either make or break our carbon budget. So if we think about our population increase and the way that we're going to urbanize over the next 30 years, we're going to see cities urbanize sometimes by 800%. And the materials we need to be able to provide products and infrastructure and other needs for just that population increase, it's predicted that if we use our traditional materials, we'll be emitting 350 gigatons of CO2 into the atmosphere. And this is a significant amount in our carbon budget.
Adam, do you see a trend with carbon material?
Yeah, so making materials out of carbon dioxide, we've seen in the last session, we're seeing it today, and I think we'll see it in a future session as well. It is an absolute trend, and for good reason. We need to start thinking not only about how we stop carbon dioxide entering the atmosphere, but how we can actually draw it out so we can limit global warming to as safe levels as possible.
Mm-hmm. Well, let's see who is our last winner for today in this category. I'm glad to announce Regional Fish Institute, Shunsuke Ishimoto, who wants to break the wall of limited supply of protein. So Frank, what did the jury like about this work and this project?
With the increasing population on this earth, we are facing the increasing problem of protein supply to this population. Yeah, and at the moment, the main source for protein supply is livestock. But livestock, on the other hand, generate a lot of problem for the environment, CO2 emission and so on. Yeah, that a good example is pig farming. That means we need to find different sources for proteins, and one of the sources, of course, is fish, but on the other hand, fish breeding takes a long period to get to new fish species, and this group now, this institute now use gene editing to accelerate the breeding of higher productive fish species, and this way attack the problem of protein supply.
Well, we are curious to watch the interview now, Adam took.
Breaking the wall of limited supply of protein. Shunsuke Ishimoto, Regional Fish Institute Limited.
Our breakthrough is a super fast breed improvement on aquatic products using the technology called genome editing. As most of you know, most of what we eat today are improved breeds, like beef, pork, chicken, corn, or anything you eat. However, the traditional breed improvement method takes about 30 years to develop a new breed, and therefore it didn't really fit the aquaculture, which has only 50 years of history. But our technology can develop a new breed in only 2 to 4 years, and therefore we can add speed to the marine food improvements in terms of quality and efficiency.
Now, why do we want to improve fish? What's the end goal here?
The one big social problem that we are facing right now is something called protein crisis. In the research, it is said that in 2025 to 2030, the demand of protein is going to exceed the supply, and we will need a good way to supply the protein to the world.
And why do you personally think that fish is a good way of getting that protein that the world needs?
Okay, there are two reasons. One, in terms of production efficiency, this is the most efficient protein source that's available in the current options compared to meat or compared to beef, chicken, or pork. The second reason is there are a lot of new technologies coming up, like insect food or something like alternative meat. But these ones, first of all, it takes a lot of cost to create some of the meat. And second of all, we still have a lot of people who are reluctant to eat them.
Can you explain exactly what you've been able to achieve so far?
So far, we have succeeded in developing 2 new breeds. One is a taiga puffer with faster growth, meaning we can ship them in about half the span than the existing breed. The second one is a sea bream with increased fillet, which we have about double the size of the edible part compared to the existing breed. And if you're able to combine these 2 traits together, technically we can improve the efficiency by 1/4.
What are the challenges getting from where you are today to getting these fish actually onto people's dinner plates around the world?
Actually, our biggest challenge is the social acceptance from the consumers. Our core technology, this genome editing, is often misunderstood as GMO, and there is a very big difference between these two. GMO it introduces the foreign genes into the organisms, and therefore it develops a completely new creature that do not exist in the nature. But on the other hand, genome editing simply deactivates existing genes, and no foreign genes are being introduced. And therefore, the developed one can be found in the nature as well, and it is just a simple shortcut of the traditional breed method. And therefore, we have to work very hard to communicate to the consumers that to make sure that they understand the difference between these two and also the benefits that this technology can bring to the world.
Well, Adam, the issue of acceptance by the people, by the consumers, is a big issue, right?
Yeah, and we see this really throughout food science. So, for example, with fake meat or even lab-grown meat, there's a big question of whether people would actually eat it. And this gives us another option, but certainly whether people are happy to eat these fish remains to be seen.
Thank you, Adam. Well, that was it with our winner session for today. You have met our top 10 winners in the category Science Startups and their stunning potential breakthroughs. Tomorrow, we will continue with the categories Science in the Arts and Digital Education. And on Monday, we will have our grand final. We will celebrate the very best breakthroughs of the year 2020 through all 10 categories. And I would like to chance and say goodbye and thank you to Frank Kalkbrenner. Thank you very much indeed for joining us and for your work as a jury chair. Thank you very much. So, Adam, thank you. Yes, thank you as well for joining me here in the studio. You will be back with me tomorrow at 1:15 p.m. We will have our next winner session, and we are looking forward to meet you again. Have a nice evening, and we will continue right now with our Q&A session. You can meet and talk to the winners directly, so don't miss that. Goodbye and auf Wiedersehen from Berlin.